Hi, everybody. Welcome to Phys 3500, Classical Mechanics. I'm your instructor, Dr. TJ Hammond. In this lecture, we'll be covering Chapter 5 and some of Chapter 8, where Chapter 5 deals with gravity and Chapter 8 deals with essential forces. Okay, so in lecture, I'll be covering, or in the tutorial, I'll be finishing off oscillations with this example of the isochrone, but I won't do that here to keep these videos nice and short. So why are we covering Chapter 5 and Chapter 8 together? So Chapter 5 is dealing on gravity, and Chapter 8 is on central forces, but it's hard to talk about gravity without talking about central forces because central forces are a very common problem, and gravity is one of the examples of that. And so dealing with planetary motion is, of course, a central force, but of course that force comes from gravity. Another example that you'll see as an undergraduate student is Coulomb interaction, so the hydrogen atom. So you have this electron orbiting around a proton. That's also a central force. Gravity also naturally leads to the idea of potentials, and so we can reduce three-dimensional problems to a one-dimensional problem by the concept of effective potentials. Potentials will also be really important when we deal with Hamiltonian and Lagrangian mechanics because we deal with the energies, and so of course the energy of the system is the total of the kinetic energy plus the potential energy, and so understanding the potentials will help us when we get to that formalism. So for the daily assignment for Monday, September 21st, please read and summarize some of these sections from Chapter 5, so 5.1, 5.2, 5.3, and 5.4. But just cover the first bit of 5.2, don't get into Poisson's equation, and you don't have to go through any of the examples, they're basically just kind of different integrals of different shapes and stuff like that. So it's not particularly interesting, and I'll go over some examples in this lecture as well. So if you just read those sections, it's only 6 pages. It's not actually that long, and you can summarize in just in very point form. So just a sentence or two for each section. So something like 4 to 8 lines long. That's all I'm expecting for this. Just some kind of evidence that you've actually read this, and so you've used these lecture notes to kind of inform you, and then you read through it and you're like, oh, that's what he's talking about. That makes sense. That makes sense. Or if it doesn't, bring that up. Okay, so as I said, we're going to be covering some of Chapter 8 here. I'm not going to be covering entirely, 2 entire chapters in one lecture, but I want to introduce some of the ideas from Chapter 8 on central forces in this lecture when we talk about gravity. So this lecture will be reviewing gravity from Chapter 5, but also introducing some of the concepts of central forces. And we'll be dealing central forces in more in-depth later on. I don't know if it'll take an entire week, but it'll take up most of the week to read to all the details of central forces, which will become extremely important when we cover Chapter 9, which is on scattering. Okay, so gravity. So central forces are any kind of force that can be written as the force vector is equal to some force magnitude, which is only dependent on the distance r, and the direction is only in the r hat direction, either to or away from this central force. So of course gravity falls under that category. So as you know from high school, this force vector is negative g(mm) over r squared, r hat. So of course the magnitude of r goes as 1 over r squared, so it satisfies that, and the direction of it is in the r hat direction, so that satisfies this central force criterion. Now this negative g(mm) over r squared is the magnitude for of gravity point particle. It doesn't necessarily need to be a particle, but it does need to be spherical. So if you were to have an extended object and try and understand its gravitational force, then you would have negative gm, where m is your test particle, maybe it's u or something like that. And then you have to integrate the density of this object, rho, over its volume v. And then you have to sum up all those little bits over that distance r squared, then that bit of that mass is to u, or your test mass, little m. So if we want to make this independent of this test mass or independent of u, who's measuring this field, we just talk about the gravitational field. Then this, we call it little g, and that's negative g times the integral of this density over r squared r hat over the volume. It's just it's the force per test mass. Good. All right, so now that we have this gravitational field, then what we want to do is get the gravitational potential. And so if we have some field g, we can write that as some gradient. So it's a negative gradient of phi, this gravitational potential. And so we integrate this gravitational potential to get that it's going to be negative g, big G, m over r, where m is the entire mass of the object. Or in more general, if it's not a some point particle, if this is some weird oblong object, then it's going to be negative g, and the integral over, oh, I have this other notation. It's the integral over the volume of this object, rho r prime over r, right? So instead of it being this integral of rho r prime over r squared, it's now the integral rho r prime over r over the volume dv prime. The potential energy is also the gravitational potential times the test mass. And so, so that's just that test mass, little m, times this phi, this gravitational potential. And so that gives us a potential energy U. And so that means the force is the gradient of the potential energy, which we knew from before. And so this force vector is negative gradient of U. Again, I won't be going through the example in this recorded session, but I will be going through it in class, and I'll have the notes uploaded after lecture where I work through this example. Okay, so now I want to talk about central forces a little bit. And so something about central forces is that, as I mentioned before, this direction of F is only going to be in the radial direction. And so there's no curl of F. So if you take the curl, or if you take this del operator in spherical coordinates, then you have this r hat d by dr, and then you have a theta term and a phi term. Well, as we know, F has no theta and no phi term, and so if you set this up properly, then you take the curl of F, and you get that this curl will be 0. So since the curl of this is 0, that means that there's nothing going around in either the theta hat or the phi hat direction. And so that means that there can't be any forces adding to or subtracting from the angular momentum. And so that means that angular momentum has to be conserved. Now, of course, if you remember, torque is the rate of change of the angular momentum, just like force is the rate of change of linear momentum. So if there's no force applied to a system, then that means that linear momentum is conserved. Just like that, in circular motion, if we have no torque is applied to this object, then there's no change in the angular momentum. Okay, so you have this object here that is orbiting around, in this xy plane, and you have it's a distance r away from this central force, and this thing's orbiting around, and it has some angular momentum L. So this will have a direction. Well, L vector is given by r cross p, so r cross this momentum, which are both vectors, and it'll be pointing orthogonal to this plane, and that's because it has to be orthogonal to r and it has to be orthogonal to p, And so this thing will orbiting in the xy plane, and so angular momentum points out of that plane. But if there's no torque, then that means that there can be no change in the angular momentum. So not only is there no torque that's, say, accelerating this thing in this xy plane direction, but also there's no torque that's changing where this L is pointing to. And so that means that this motion will always lie in the same plane. So not only will the magnitude of L not change, but also the direction of L won't change as long as we have no torque. And if it's a central force, there is no torque applied. Okay. So we have this object, as I said here. Now, this object, initially, we have this as a central force, and so this thing is moving in 3 dimensions as we have this del operator that it's an r hat, theta hat, phi hat. So this thing's actually moving in all 3 dimensions in space, but by recognizing that with a central force, the angular momentum is conserved, the L direction doesn't change, and so that means that this object has to be in a plane, so it has to be in this xy plane. So we've now reduced this 3-dimensional problem that this object could be moving in to a 2-dimensional problem where it has to be going in this xy plane. Now we can further this idea from 2 dimensions to 1 dimensions by introducing the concept of the effective potential. So the force is only in the radial direction, so it's a 1-dimensional problem, right? But the particle right now is we're describing it as an x and y, or r and theta, which is of course 2 dimensions. So we want to simplify this to the 1 dimension that the force to a 1-dimensional problem, because the force is only a 1-dimensional problem. So if we take the kinetic energy, of course, kinetic energy is 1/2 mv squared. But what does v squared actually mean? It's the velocity dotted with itself, where in polar coordinates, the velocity is r dot r hat plus r theta dot theta hat, and this we derived last Friday's lecture. So this is the velocity represented in polar coordinates. Now, 1/2 mv squared. So r hat and theta hat are orthogonal to one another. So when we square v, what we get is r dot squared and r squared theta dot squared. So that's because r dot theta, or r hat dot theta hat is equal to 0. So any of those cross terms actually go away, because this is the dot product, and so the dot product of orthogonal vectors is 0. So the total energy is just like what you would think. It's the kinetic energy plus the potential energy, and so 1/2 mv squared plus u. But we can now write this kinetic energy is 1/2 mr dot squared plus 1/2 mr squared theta dot squared. So that's just kind of squaring the 2 parts of the velocity, plus this potential energy, which is only a function of r. Now, we learned from before in the previous slide here that the magnitude of L is mrv, or mr squared theta dot. So we can rewrite theta dot as L over mr squared. And so we can substitute this theta dot, this definition for theta dot, into our equation, and we get that the total energy is 1/2 mr dot squared plus 1/2 mr squared times L over mr squared, all squared, plus ur. Some of those r squareds cancel, some of that m cancels, and so what we're left with is 1/2 mr dot squared plus L squared over 2mr squared plus ur. Now, the first term is just going to be some velocity. We have some rate of change of this radial direction, so that's like a velocity, and everything else is just r dependent. It's independent of the velocity. And so we can just lump that together, and we call that the potential. And so now the total energy of this 3-dimensional problem is reduced to 1/2 mr dot squared plus u effective. So it's much more in line of saying this is 1/2 mv squared plus potential energy, where v is only in the radial direction. Okay. So now we have a kinetic energy that's only dependent on the velocity in the radial direction, and a potential energy that's only dependent on the radial direction, but this potential energy is this effective potential energy because it includes this angular momentum part. So what does that look like? Well, as I said, we're talking about gravity here. So what happens in the case of gravity? What we get is the potential energy of gravity is negative gmm over r, and so that's given by this green dotted line. And we also have this other part of the effective potential, this angular momentum part, and L squared over 2mr squared, and that is positive, of course, and it also blows up as r approaches 0. But you might recognize that as r gets very, very small, the 1 over r squared part gets much bigger than the 1 over r part of the gravitational potential. And so that means that as we get really close to this central object, to the central force, the 1 over r squared term will dominate, and so that means that the total energy becomes positive. If the energy is positive, then it's repulsive, but then as we go farther away, you see that the 1 over r term dominates compared to 1 over r squared, because 1 over r squared gets smaller faster as you increase in r. And so that means that at a certain point, this attractive gravitational potential will dominate. And so what this is saying is that the total of the green dashed line, the real potential of gravity, and this orange dashed line, which is the kind of like centrifugal part of the effective potential, you combine these two things together to give us the effective potential, and that's given by this blue line here. And you can see that when you're too close to this object, to the central force, that the energy is positive, and then as you increase, this energy is negative, and that means it's actually attractive. And for a region there, you can see that this thing kind of looks like what we saw before with the harmonic oscillator, that this has a little bit of a minimum here. And when this has a minimum, it looks kind of like that harmonic oscillator. Okay, so done is we reduced a three-dimensional problem down to a one-dimensional problem where we're representing it in this kind of this energy versus distance space. So if we look at some different cases, as I said, if the energy is positive, we're in case 1. And that's like what we have here on the right, where we have case 1. And that would be, say, if this were a gravitational object. So this thing in the middle is, say, the sun. What this would be like is if we had an asteroid coming in from, or a comet coming in from interstellar space, and it comes in with way too much energy, comes close to the sun, and then just keeps going, out to infinity. So that's what's saying here is this object has come in from infinity. It gets attracted to this, but then this repulsive angular momentum part is too great, and then that throws that back out, and this thing goes back out to infinity. You can also have case 2, where you have a very weird bound orbit, and so it starts off from really far away. It comes in to some close distance, but then again, that repulsive centrifugal energy throws it out, and this thing oscillates between some minimum r and some maximum r. And that's what we have here in green. So it starts out, quite far away, and this orbit, this object, this planet is orbiting this this sun in this really elliptical orbit here, and that's what this is saying in the xy plane. And case 3 is kind of like what the Earth is around the sun. We're right near this minimum of this potential. So as a function of r, this is basically just constant. So this object is always basically the same distance, but in the xy plane, what that means is r is constant, and so this distance is the same, and this is basically just a circle in the xy plane. Okay, so that's the purpose of the effective potential, is trying to explain this motion in the xy plane is actually quite complicated. We looked at conical sections last year, and we'll be looking at them again this year. But this is quite complicated to describe it. But if you have this plot here of this effective potential, it's actually quite easy. All you need to do is know what the energy is, know what your effective potential is, and you can actually find what your minimum distance is, your maximum distance is. and all these kind of properties. So something I want to finish off with today are tidal forces. I always thought these were kind of neat. So we have central force. In general, we have the acceleration as r double dot minus r theta dot squared. So if you remember that from last Friday. So what we get is, just like we had before, an effective potential, we have an effective force. So this force of this central force is going to have not only the acceleration in r, so that's mr double dot, but also this tangential bit, which, well, sorry, not the tangential, but the centripetal bit, which will depend on the angular velocity, and so that's mr theta dot squared. So we can make this effective potential, the effective gravitational force as negative gmm over r squared plus mr theta dot squared. So remembering that negative gmm over r squared, so the fact that it's negative means that it's attractive, right? But now this effective force actually has this positive term, so we have something that's actually repulsive, so mr theta dot squared. And so that means that if we look at this Earth on the moon, if we actually look at the gravitational force, then the force at B is, the magnitude of the force at B is greater than the magnitude of the force at A, and that's because R is smaller, right? And so that means that the force on these 2 points aren't the exact same, okay? Also, you'll have a force at C and a force at D that will be pulling towards the moon. The magnitude will be the same, but there'll be a leftover component that pulls towards the center of the Earth. And so basically what that means is that you have points C pulling down, you have point D pulling up, and point B pulling to the left, and point A not pulling to the left as much. And so if you take the total forces from the center of the Earth, you'll see that B is pulling slightly to the left, A is actually pulling slightly to the right, C is pulling slightly down, and D is pulling slightly up. And so since the Earth isn't a perfect hard sphere, there's water, there's also like a mantle, and there's a soft core, things actually distort a little bit. And so it turns out that the easiest thing to distort is, of course, the water. And so it ends up being that this water gets pushed around a little bit, caused by the moon. And so that's what causes tides. So it's the result of a distortion of the planet, the result of the differences, the tiny differences of these forces throughout the surface of the Earth. After this, we just have problems, and so this will be covered in the tutorial. But for this is just a lecture. So, all right, I hope that we'll be able to see you during lecture, but if you, for some reason, you don't have internet access or something, you can still view the summary of these slides here. All right, and I'll see you in lecture.